Welcome to the second part of the lecture problems for Chapter 4. Here, question 5 says, a ball is tossed from the top of a building at an initial velocity of 8 meters per second, angled 20 degrees below the horizontal. It strikes the ground 3 seconds later. The first thing we're asked to solve for is how far horizontally from the base of the building does it land, from what height was it thrown, and how long does it take for the ball to reach 10 meters below its starting position. All right, so let's make a note of the quantities that have been given to us. The initial velocity is 8 meters per second, but because it is angled downward, when we determine the components of this initial velocity, here, x-axis, here, negative y-axis, let's label it x, negative y. Here's v initial. You can see the angle 20 degrees is with respect to the x-axis. So VIX, the initial x, is positive, it points to the right, but V initial y is negative since it points downward. So here we're going to go ahead and write the components of V initial in both x and y. 8 meters per second times, the cosine of 20 degrees, or minus 20 degrees, which still yields a positive number. And this gives us positive 7.52 meters per second. V initial y, on the other hand, 8 meters per second times the sine of minus 20 degrees, which of course will be a negative number. So we'll go ahead and put that minus there. The initial y will be minus 2.74 meters per second. We are told that the ball strikes the ground 3 seconds after it's tossed. So let's just go ahead and see what the trajectory of this ball might look like from its launch to the striking of the ground, which would be right here. So t is equal to 3 seconds at the time it strikes the ground. Well, the horizontal displacement, which is the first thing we're asked to solve, delta x will be equal to v initial x times t, the time to strike the ground. Since we've already obtained v initial x, we multiply it, that's 7.52 meters per second, multiplied by 3 seconds, and that gives us a delta x, horizontal displacement, 22.6 meters. Now, the next thing we're asked to solve for is from what height was the ball launched? In other words, what is y initial? Since we are told to take y final to equal 0, that is ground level, we set this equation equal to v initial y times t minus a half g t squared. And we proceed to solve for y initial in the case where t is equal to 3 seconds. And of course, notice there's a negative sign here, which we will have to then transfer to the terms on the right-hand side. That gives us an initial position of 52.3 meters above the ground. So the starting position of this ball was 52.3 meters. It flew, the time of flight was 3 seconds before striking the ground. The next part of the problem asks us to determine what time, how long does it take when the ball is 10 meters below its starting position. So in other words, when delta y is minus 10 meters, what is the value of t? Now we know that it should be less than 3 seconds because after all, it only takes 3 seconds to fall 52.3 meters downward. 10 meters should take less. So we set minus 10 meters, and remember we have to indicate that it's a negative displacement from its initial position. So we must always use negative signs to indicate negative displacements. And what we see here is that we are left with a quadratic equation. And so we set up the quadratic equation minus 2.74 meters per second, which is minus b. And remember that b would be v initial y with a negative in front of it, but because v initial y is negative itself, negative times negative gives us a positive b. And so in the quadratic, minus b is then minus 2.74 plus or minus square root 2.74 squared minus 4 times a. A here is 4.9. It's a half g times delta y. And our delta y is negative. And so we must write it as a negative number, knowing or noticing that these two negatives will cancel, divided by 2a, which is 9.8. This gives us a value of t of 1.18 seconds, which absolutely agrees with our prediction that a displacement of 10 meters downward should involve a time period which is smaller than 3 seconds. Next problem. Here, question 6 says, what is the centripetal acceleration of a point on the surface of the Earth at the equator due to the rotation of the Earth about its axis? We are told that the radius of the Earth is 6.37 million meters, or 10 to the 6 meters, and that it takes 24 hours for the Earth to complete one rotation about its axis. So, we are solving for the centripetal acceleration of an object or a point or anything on the equator, given that the radius of the Earth at the equator is 6.37 e to the 6 meters, and that the orbital period of the Earth, 24 hours, when we convert into seconds, is 86,400 seconds. Well, we know that centripetal acceleration is given by tangential speed squared divided by radius. Now, we also know, and here the radius would be the radius of the Earth, the radius of rotation. We also know that the tangential velocity is related to the orbital period by 2 pi r, here the radius of the Earth, divided by t. So we can make that substitution, square both sides into our expression for centripetal acceleration, and so we get 4 pi squared, radius of the Earth squared, but notice that that term divided by orbital period squared, but notice we have a radius of the Earth here, and so that will cancel out. This will be canceled out by that term. We plug in all of the numbers, and in fact we discover that this is quite a small centripetal acceleration, and in fact for the most part we neglected anytime we consider the acceleration of an object on the Earth, we do not take into account the contribution of the Earth's own centripetal acceleration due to the rotation. We tend to neglect this term. However, in terms of accuracy, we should consider it when we get to Newton's laws, where we look at the normal force as a force of support against the weight of the person. We in fact discover that we can, if we take this term into account, we find that the normal force is actually a little bit affected by this term if we were to truly consider it. And this leads to a discussion of inertial mass versus gravitational mass. But we won't pursue that any further here. Let it just be known that the centripetal acceleration of objects on the surface of the Earth is a small value. Next problem. Here, question 7 tells us that an astronaut is holding on to a satellite which is in circular orbit at an altitude of 600 kilometers above the Earth's surface. Here, the value of g, which is related to centripetal acceleration, is 8.21 meters per second squared, again, the radius of the Earth. We're asked to determine the orbital speed of the astronaut satellite and the orbital period of the astronaut satellite. Well, let's see. H is given to us as 600 e to the 3 meters. The radius of the Earth, 6.37 e to the 6 meters. And the centripetal acceleration, or in other words, the effective gravitational acceleration at this altitude, is 8.21 meters per second squared. So, to obtain the tangential velocity, we make use of the relationship that Vt squared over t, the orbital period, Vt squared over r, the radius of the Earth, is equal to centripetal acceleration. So when we solve for Vt, we get centripetal acceleration times the radius of the Earth plus the altitude. You see, we have to take into account the actual position of the astronaut and satellite relative to the center of the Earth. In other words, little r is radius of the Earth plus h. We substitute our numbers and we obtain V tangential as 7,560 meters per second. And in case you're wondering how fast that is, it's about almost 17,000 miles per hour. That is pretty fast. And in fact, what we'll find is that the orbital period will be under 2 hours, or in fact, just over an hour and a half. That's how long it takes for the satellite and the astronaut to orbit, to complete one orbit about the Earth. Okay, let's substitute in our values. 2 pi, radius of the orbit, divided by the value we just obtained for the tangential velocity, and we find the orbital period in seconds is 5,790 seconds, and converting this to hours, we find that it's 1.6 hours, roughly speaking. And so you can see that the motion is quite rapid. Well, this concludes the last part, or part 2, of the lecture problems for Chapter 4. See you next time.